Okay, welcome everyone. Thank you for coming and welcome to today's NAGT webinar, which is sponsored and presented by GETSI. And so thank you again for coming, and we're looking forward to this webinar about teaching about the water cycle and data-rich water resources activities coming out of GETSI. Just a reminder, if you haven't had a chance, or you can do so quickly, take a peek at your Zoom controls, and particularly if you can locate the chat function there, as you see on the ribbon, that little chat button. We'll be using that throughout the course of the webinar. In particular, if you have any questions throughout the course of the webinar, please enter them into the chat box, and we can kind of queue them up as we go and answer them at various stopping points in the course of the webinar. So Beth, if you want to move us forward a little bit.
Sorry, it wasn't responding. Okay, there we go.
Okay. Fantastic. So this is an NAGT webinar series. So welcome for coming. And so NAG sponsors this comprehensive webinar series, which is hopefully your one-stop shop for strengthening work in Earth education. Webinars are featuring novel and innovative work in Earth education research and pedagogy, new teaching materials, as we're talking about today, in classroom and professional experiences of people like you. Right? So this webinar is really built by the community and folks like you. The webinar series is free, and we encourage you to invite your colleagues to attend and join the discussion. All of the webinars are recorded, so you can go back and see all the different webinars, which are now over 100 or so, through the archives. You can also see upcoming schedule of webinars by going to the website. And if you have ideas, you can certainly submit ideas for new webinars. We're always looking to hear what the community wants as we plan for next year's webinar series.
All right, thanks, Andrew. My name is Beth Pratt-Sitola, and I am the project manager for GETSI, which is GEodesy Tools for Societal Issues, one of multiple projects that help to make the NAGT webinar series possible. The teaching module that we'll be talking about today is Eyes on the Hydrosphere, Tracking Water Resources. And after I give a sort of an overview to GETSI and a bit about the data, then you'll hear from Becca Walker, who is one of the authors of this module and a co-PI on the GETSI project. All right, so overall, the GETSI project has a mission to develop and disseminate teaching and learning materials that feature, within the broad suite of types of data, geodesy data, and especially quantitative skills applied to critical societal issues such as climate change, water resources, and natural hazards. It's a sister project of the Integrate project, which you might have heard of, which is doing a number of modules related to sustainability and interdisciplinary earth science. GETSI has been funded by 4 different NSF grants, and in total has developed 13 modules of roughly like 2 weeks each. They both introductory and majors level, both classroom and field, but today, of course, it's an introductory classroom module that we'll be describing. To make sure we're all on the same page, though, quickly, geodesy is the science of accurately measuring the Earth's size, shape, orientation, mass distribution, and how these change with time. Traditionally, just simply surveying, was hard enough. The precise positioning of points on the Earth was what geodesy could achieve. But more recently, there is really, in the last few decades, a toolbox of techniques to better measure the Earth, and especially our understanding of how things change with time. If we think about unpacking that toolbox, it includes things like the GPS, Global Positioning System, INSAR, which is the radar satellites. Repeat measurements can see deformation over regional areas. This is showing an earthquake. High resolution topography, be it from LiDAR or from photogrammetry, structure from motion photogrammetry, any high resolution topography that helps us see the surface of the Earth and how it changes. Strain meters, tilt meters, creep meters, gravity measurements, especially these gravity satellites, the GRACE and the GRACE follow-on, and sea level and ice altimetry, again, usually satellite-based, sometimes airplane-based. So there's many things in this toolbox. And then when it comes to thinking about the modules themselves and the philosophy that's going into them, all of the GETSI modules, including the one you'll hear about today and the integrate modules, have the guiding principles of addressing one or more grand challenge facing society, making use of authentic and credible data, in this case GEodesy data, improving students' understanding of the nature and methods of science, how is science conducted, how do you communicate it when you feel like you found something, and some deeper, more authentic way to approach interdisciplinary problems. And I think of this as applying geoscience learning to social issues. So it's not enough to say that an earthquake can knock down a building and then let's move on and talk about physics for, geophysics for a long time, but they really have to take that and apply it to something related to policy or economics, so that we can work towards better societal decisions. And especially for the GETSI project, quantitative skills is really emphasized. Whatever level is appropriate for the students. For intro, that might be quantitative, reading graphs or quantitative maps correctly. For a majors level, it goes higher than that. The modules are developed following the process of assessment and development and assessment by the Integrate project. It's backwards designed, so it starts with the learning goals, moves on to the more granular outcomes. Then you need to think about, like, how would you know if the goals and outcomes have been achieved? So you determine your assessment strategy, and then you move on to designing the teaching materials and instructional strategies to match. All of the modules are pilot tested and then revised before publication. So just to make sure that you're comfortable with the controls, if you have had a hard time seeing them, you might need to shake your cursor around near the bottom of your screen and a black bar will appear. So how about go ahead and raise your hand if you already use any geodetic data in your teaching. And those will appear. So we have 5, 6, 7, 8, 9, people have raised their hands so far. And if you're looking at the participant window off to the side, those will start to appear. Yes, so we have a good selection, I think, of about 10 or so people out of the 40 that are on. So you can go ahead and unraise your hand now. Okay, thanks. And now we're going to do the first poll. And so just to practice using that, but I have it on the screen here, but Andrew will also pop the poll up so that everybody can see it in a moment. All right, there we go. So you can go ahead and vote. Which of the water resource monitoring methods you know least about? So vertical GPS, GRACE gravity, reflection GPS, or SNOTEL. So we'll give that a moment to settle down. Okay. I'm going to end the poll and share the results. So it looks like we have vertical is sort of a sub-equal GRACE and reflection GPS, and also a couple people mentioned vertical GPS, but the majority was SNOTEL, and that's actually a more traditional method, but many people haven't encountered it. So we'll mention it as we go along. So, okay, thank you for participating, everyone. We'll have more opportunities for that. One thing I do like to mention at this point is it's really handy to keep a set of notes, maybe a piece of paper or however you like to take notes electronically off to the side, so that as you're going along, if you see things that are of particular interest to you, or like, ooh, I would like this, but I need to change it, like, then you can, and then Becca will be asking you some questions later, you can go ahead and jot that down. So I'm going to run through an overview of some of the different methods that the students encounter and that are included in the module. So we're going to start with high precision vertical GPS. So GPS is, they're all around us. We have them in our phones, in our pockets, in our watches. And so this is actually a great entry point for engaging students. That can be a fun part of it. There are actually thousands of GPS stations, permanent GPS stations across the US. Some of them are real time. Most of them have a latency of about a day. And it turns out that the vertical position, the solid earth responds elastically to changes in load. So that changes from groundwater pumping or drought or ice, in that case, you get a near instantaneous reversible linear accommodation from the surface. So what this looks like, if we're just pulling a station here from the Western US, this is showing you north, east, and vertical. So for water related things, it's really the vertical that we're most interested in. And you can see these cycles in the vertical position are almost, and they cycle in the year. And then you can also see changes which generally reflect wetter, drier cycles. And so this has been extremely informative for the water cycle. Turns out that GPS can also be used for something that nobody ever guessed at the beginning, and this is reflection GPS. The idea being, generally GPS stations are designed to listen to the direct signal, but actually what was once thought to be only noise, the signals that bounce off the ground and come back turn out to have quite a bit of information in them. So for instance, if it snows, that signal is going to be changed. And you can see that they haven't successfully filtered that out, fortunately, and now they find it to be information. So changes in snow or other things such as vegetation. And so it changes the signal in different ways. So for instance, in snow, it offsets the phase, vegetation changes the amplitude, obviously if it's not in a parking lot or something like that, and soil moisture also will change the phase. Another type of very powerful for the ice and water system measurement is the GRACE missions, which is the Gravity Recovery and Climate Experiment. The original GRACE ran until 2016-ish, 2017, well over its original 5 years. And the GRACE follow-on mission was launched in 2018 and data is flowing now. The gist of it is that there's these two satellites that are orbiting the Earth in tandem, and they have a laser between them that measures very carefully how far they are apart. Obviously, this is greatly exaggerated here, but what happens is the first one will feel a mass sooner, and it will speed up a little bit, and the distance between them will lengthen, and that will remain farther until this first satellite starts to leave from that mass zone, if you will, and then this one is still traveling faster, and so they get closer together again. And so by processing this information, we're able to see a lot about how the mass changes. So for instance, this is about a decade of groundwater changes in the US. You can see that there has been a loss of mass across the southern part, and actually a gaining of mass, particularly in the Dakotas and Nebraska. Globally, you can see similar things. This one has actually been altered to take out Greenland and Antarctica because that will totally skew the picture. But you can see glaciers in Alaska, groundwater in California, and other basins, how it's coming and going. The module also deals with 3 more traditional water measurement methods. So that would be stream gauging, like just simply the level of water, surface water. There's groundwater wells, so the level of groundwater, and SNOTEL. So I'll spend a moment on this since people weren't sure what it is. So these are snow pillows. And so there's like a glycol or something in here. And as the snow piles up, the pressure sensor in the bottom of the pillow can tell approximately how much mass there is. The challenge with SNOTEL is that it's very point measurements and snow drifts around. And so that can be a time when it's difficult with the limited number of stations to make a regional estimate of snow. GPS is also a point measurement when we talked about the vertical GPS, but it actually integrates over a larger area of reflected data back to the GPS. So it integrates over a somewhat larger area than a snow pillow. Yes, I would say generally at this point, I will hand it over to Becca, but if people are having any technical questions, there'll be another chance at the end, but feel free to use that chat box and put in anything that you have questions, and we'll address them either as we go along or at the end as it makes sense. But I am going to stop sharing now and pass it over to Becca, but I'll keep an eye on the chat box.
Thank you, Beth. Okay. Hi, everybody. Thanks so much for attending the webinar this morning. My name's Becca Walker, and I am one of the authors of this Eyes on the Hydrosphere module, along with John Harvey at Fort Lewis College. And the first thing that I wanted to reiterate is that although the Eyes on the Hydrosphere module is for intro level students, the work that John and I did in developing this intro level module is based on another existing GETSI module for majors and upper level students. So there are also water resources, GETSI materials for the upper level crowd, if that's an audience to whom you're catering in your classes. But we'll focus on the intro materials today.
Hey, Becca, sorry, just to jump in. One thing I forgot to say was that people are welcome to go to the webpage. So if you just search for GETSI and CIRC, it'll come up. And so if there's anything you want to follow along, either the intro or the majors level, people can do that.
Yes, and and on one of the subsequent slides, I have a link to the Eyes on the Hydrosphere module homepage, so you can navigate from there also if you'd like. So I wanted to start by looking just very briefly at the sort of overarching module goals for Eyes on the Hydrosphere. And you'll see these goals sort of manifesting themselves in the exercises that students will be tackling in the context of this module. So analyzing major reservoirs and transport pathways of the hydrosphere, we will be looking repeatedly at 6 traditional and geodetic means of measuring their relative contributions to a water budget. I'll also show you this morning some examples of student opportunities to interpret these real geodetic and traditional data sets from a couple of different case study areas in Unit 2. And then finally, we're linking the societal piece and the societal evaluation of changes in water supply and demand throughout the module. And these 3 photos that you see at the bottom of the screen are 3 of the 6 methods that we'll be looking at as we move through the module. So as Beth mentioned, if you're interested in adopting any of the GETSI modules sort of wholesale, expect this to encompass 2 to 3 weeks of class time. But all of the GETSI products are designed so that if you're not looking for 2.5 to 3 weeks of material, which I think most of us are not, but instead you want to pull a 30-minute or a 60-minute exercise, or maybe you're looking to put a new lab into your curriculum, this module is designed so that you can either pull a portion from maybe 1 or 2 of the units, or use an entire unit if that's something that you're more interested in. The Eyes on the Hydrosphere module is broken up into 3 units. We will spend the most time together sort of interacting this morning with Unit 2, but I definitely want to give you an overview of Units 1 and 3 as well. And then again, all of the teaching materials, including exercises, PowerPoint slides, teaching tips, answer keys, etc., can be found on the module page. So starting with Unit 1, which is exploring the reservoirs, pathways, and methods to measure the hydrologic cycle, you perhaps want to pitch this as a preparation exercise for your students. And so to set the stage, we have some pre-readings on Los Angeles, Las Vegas, and Salt Lake City, and the unique water-related issues that each of those cities are experiencing that you can have students read. And this Unit 1, it's kind of a reimagining of how you might want to teach the water cycle. Because I can say for myself that prior to being involved in developing these materials, the way that I would teach the water cycle is I would pop up an image from their textbook with a bunch of reservoirs and arrows on it. We would talk through it together for a few minutes, and then I would kind of call it a day and move on to something else. This part of Unit 1 is a way to give students a little bit more ownership over populating a water cycle diagram like this one that you see at the bottom of the screen. And this is available on the GETSI page in color and black and white. So if you're doing this as a pre-assignment, you give the students this diagram and ask them, hopefully without using their textbook or the internet, to populate this diagram with as many what we're calling reservoirs and transport pathways that they can think of. And then when they come back to class the next time, you can either walk through this diagram with them as a whole group discussion, or if you have time, maybe you pair students up so that they can compare notes with a colleague and potentially make some modifications. And it looks like somebody's lost sound.
I think it might have been isolated.
I understand. Okay, so here's the figure that's available on the GETSI page for this exercise. And then here's an example of some student work from when I pilot tested before we did the group discussion about reservoirs and transport pathways. So now that they've looked at the major reservoirs and transport pathways, now we move into this discussion about how scientists using traditional and geodetic methods might measure short-term and long-term variability in these reservoirs. So in this yellow box, these are the 6 methods that we're going to see coming up over and over. The stream gauging, depth to groundwater, and SNOTEL, we're considering the traditional methods. Our geodetic methods are GRACE, vertical GPS, and reflection GPS, which Beth discussed earlier. So in preparation for this next part of Unit 1, each student is given a 1-pager on one of these methods for measuring the hydrosphere. So here's the vertical GPS example, and these are all on the module web page. Each 1-pager includes an image of the method, how it works, an example time series, and then a link to some kind of multimedia from them to watch. And they are instructed with some guiding questions to be prepared to teach other people about their method during their next class meeting. So now we come to class, and my recommendation is that you start by putting all the GRACE folks, all the SNOTEL folks, all the stream gauge folks together so that they can spend a few minutes conferring with colleagues, and so that you have an opportunity to walk around, do a little eavesdropping, and make sure that there are no major misconceptions that will be subsequently propagated to the new teams. The new teams, you can see it on the bottom of the screen. So this is a jigsaw that we're setting up. The new teams will have at least one representative from each of these 6 methods. And then each student in each group will give a brief informal presentation about how their method works. Depending on your time constraints, you can then wrap up with this exercise with some example data sets for 5 of the 6 methods. So here's an example time series for vertical GPS. And you could run this where students just have this as a handout and they're working with this in their groups. You could also run this as a gallery tour where you have each of these time series examples hung up on the wall with the questions that go along with them, which I'm putting on the screen now. So if you're doing it as a gallery tour, student groups could go from data set to data set, and for each one they need to decide which method is being illustrated in the time series, how they came to that conclusion, and then there are some questions thinking about long-term variability in the data and having students think about some environmental and/or human factors that might cause these data to vary over the course of the time series. So that's Unit 1. For assessment purposes, you maybe want to finish with students going back to their original water cycle diagram and now adding the methods, the traditional and geodetic methods to their diagram, illustrating which of those reservoirs each method is best for assessing. So this could serve as a nice summative assessment for the instructor to sort of assess what students took away from Unit 1. Next, I'm going to move on to Unit 2. And Unit 2, we've broken up into 2 geographic case studies, the first of which I'm just going to mention in passing, and that's all we'll say about it during the webinar. So if you're interested in students working with SNOTEL, reflection GPS, and stream gauge data, you might consider implementing Unit 2.2, which is looking at a study area in Southwest Colorado, which we're calling a Western Mountain Watershed. So the other thing that's handy about Unit 2.2, in addition to looking at those specific data sets, is that the 2 stations that they're looking at that you see marked in green, there's one that's upstream of the Vallecito Dam, and the other that is below the dam. So it's a nice opportunity for students to see how infrastructure can have a real impact on seasonal and annual signals in this area. The one that we're going to put some more work into this morning is Unit 2.1, which is tracking water resources in the High Plains Aquifer. And the data sets that are featured in this portion are GRACE, vertical GPS, and depth to groundwater. And I want to step you through kind of our motivation for why we've devoted such a big chunk of this module to the High Plains. So the study area is shown there. You can see that the geographic extent of the High Plains Aquifer is pretty substantial. So it involves 8 states in the US. And from a food security and sustainability perspective, this has a huge societal importance, as roughly 1/3 of American irrigated cropland is irrigated with water pumped from the High Plains Aquifer. So because of that, there's pretty excellent data coverage for our purposes and what we're trying to do. Pedagogically, this is an excellent opportunity in this case study for students to interpret hydrologic time series data, look at seasonal, annual, and longer term patterns, and ultimately articulate some of the environmental factors that are influencing water availability. And the red circles that just came up on the map to the right, the lower circle is the vertical GPS station that we really won't be spending any time on this morning, but we will be looking at those GW1 and 2 stations that are circled right now. Before we do that, I'm going to pause here for about 30 seconds so that you can look at this data set from the US Drought Monitor. So the legend is there, but I've also noted it in bold under the time series. We're looking at data from 2000 to 2019, and the periods with the most orange to red to maroon colors are the times of the most exceptional or severe drought. So I'm going to pause for about 30 seconds, and in that time, I would like you to scribble to yourself, identify 3 periods that to you looked to be particularly dry in the High Plains Aquifer. Okay, so I hope that you've made a quick note to yourself, because you'll be asked to refer back to those 3 periods that you identified as particularly dry as we move forward. So now we're going to spend a few minutes with Unit 2.1. And so ultimately what's going to happen is that you'll be provided with some time series data for those 2 well sites, GW1 and GW2. And I want to tell you that this is a tiny excerpt from Unit 2.1. And if you want your students working on this using Excel so that they can use the hover feature, that's definitely feasible. I will say that personally, when I pilot tested the module, I was doing it in a study abroad program where most students didn't have a laptop. So this is definitely also totally doable using these data sets you're about to see in hard copy. So here's some depth to the water table data for GW1. We've got time on the x-axis, and you can ignore the right-hand y-axis, which is the GRACE data. We'll superimpose those in a couple of slides. But I like to pause for about a minute, have you look at these groundwater data and write down for yourself a quick description of any annual and or seasonal cycles that you see in these well data. And then I'd also like you to cross-reference those super dry years that you identified a couple minutes ago and make a couple notes to yourself about how the water table data look in those particularly dry years. So I'll be quiet for 1 minute and then we'll move on. Okay, this won't be the last time that you see GW1 if you're not quite done looking at the time series, but I'm going to advance to the next slide and I'm going to now show you the GRACE data superimposed on this plot. So this time series shows depth to groundwater and GRACE. So when you're thinking about this next question, and again, making some notes to yourself, I'd like you to jot down some thoughts about how the GRACE data in orange seem to compare to the depth to groundwater data that you just looked at. Okay, here's our second station, GW2. So same deal as what we just did for the GW1 station. I don't have any GRACE data up right now. We're just looking at depth to water table on the y-axis and that same time period on the x-axis. So just like you did for GW1, take a look at the shape of the data and write down for yourself any annual and or seasonal cycles that you observe in these well data. And then again, please go back to those years you identified as the ones with the more significant drought and take a look at how the water table for this station responded in those years. And I'm pausing again for 60 seconds. So I think you know where we're going. Let's take a look at the GRACE data now for GW2. So again, we've got a time series showing depth to groundwater in blue, GRACE in orangish. Take a little bit of time and scribble down for yourself how the GRACE data seem to compare to the depth to groundwater data for this station. Okay, so I'm sure that was nowhere near enough time, and obviously nowhere near the amount of time that you would give students to interact with these data. But we have a second poll for you now that you've had a couple minutes to puzzle over GW1 and 2. And I think, Beth, you're going to talk about this poll.
Sure. Yeah, and Andrew will pop it up momentarily. All right, so we have which well has more regular annual or seasonal cycle, which well has a more pronounced long-term change, and which well seems to recover recharge more quickly from declines. So go ahead and enter in your answers. All right, I think we'll go ahead and share the results now, even though I know not everyone has done it. So,
Interesting.
Yeah. So which has a more regular cycle? Groundwater well 2, both of them have cycles, but yes, I would agree that it's more regular for the second one. More pronounced long-term change. Yep, you'd get a much better R squared for groundwater well 2, and which seems to recover more quickly from the declines. Everybody is saying number 1 in that overall, if you took an average, it probably hasn't changed terribly much. Awesome.
And I want to just add that if you're looking to infuse more quantitative skills into your teaching, this is, again, just a very small excerpt of how you could play this out in your classroom. And there are a lot of quantitative questions that go along with supporting this qualitative work that we just did together. I'm going to pop up a fourth question and ask folks to consider it for a minute and then enter some thoughts into the chat box. We're also interested in the relationship between the GRACE data and those 2 groundwater wells. So any thoughts that you have about how the GRACE looks maybe compared to the depth to water table data for GW1 and or GW2, we'd like to take some comments in the chat box. So we've got several thoughts coming in about better correspondence in the seasonal patterns for GW2. GW1 being an overall better match. For GW2, both have a decreasing trend line. There's someone who's mentioning why the GRACE data for GW2 why it didn't follow a similar pattern to what they're seeing in the groundwater data? What a great question. Maybe your question will be answered in the next slide. In GW1, Grace and the depth to water table have some agreement between 2008 and 2018. So Beth, do you want to address any of these questions, or do you think it would be good to move on to our next slide?
Maybe I'll just say a couple things. And so
Great.
I think one of the wonderful things here is that it actually introduces students to the complexity of real life, and real data. And I think there's a variety of things that people are noticing, but I think we could possibly, hit on a couple, which would be some of the year data, like where in groundwater one plot, like where it seemed like if you were going to say, hey, do I see the droughts? Like there's evidence, I'd say, that both the Grace and the groundwater one are showing some lower water times at the same. But that if you were to take an average through the Grace data, it does seem to be trending downwards in a way that groundwater 2 is. So it's like maybe Grace is reflecting both of these signals kind of in a mushed together way a bit.
I'm also looking at one of the comments that just popped up in the chat box where someone's mentioning that if you look at the y-axes for both of these, depth to groundwater is only about 10 feet in GW1, whereas in GW2, it's more like 140 to 150 feet, 10 times deeper. So I think that that's a great segue to looking at this next slide, saying, hey, why the difference in pattern between these two groundwater wells? So there's a location map again to remind you that spatially they're pretty close to one another. But if we look at the well descriptions, and I've circled kind of the relevant aha here, GW1 well depth is 20 feet. 2 is 175. So the deal is, it kind of depends on how you want this to play out in your classroom and what your instructional objectives are. You could give students these well descriptions at the onset and say, we're going to be comparing a shallow versus a deep site. You could also do it the way that we've done it, where they don't, unless they're shrewdly looking at the y-axes and they notice that this is a shallow versus deep site, which frankly my students did not. Maybe you have them look through the time series like we did first, and then toward the end, like we're doing, then you say, hey, what's the difference? Let's look at the well descriptions, and aha, these well depths are drastically different. So any way you slice it, Unit 2.1 is a nice opportunity for your students to have the opportunity to compare groundwater trends from the shallow rechargeable aquifer GW1 versus the deeper rapidly depleting aquifer GW2. And if you're interested, we're not going to hit this today in the webinar, but there's a section from the High Plains Aquifer case study where they can look at some vertical GPS data. And for the societal component, we've got qualitative and quantitative questions throughout Unit 2.1 that are getting at the societal relevance of understanding the short-term and long-term trends and health of the High Plains Aquifer. So I hope you'll consider adopting part of this case study in your class. Moving on and finishing up with Unit 3, I'd like to talk for just a moment about Unit 3.2, which is called What's in Your Watershed. This was a pretty big gamble for me personally when I was helping to develop these materials, because as someone who really didn't have a lot of experience personally accessing these data, to put it in the hands of the students and say that in 3.2, students are going to be accessing and interpreting hydrosphere measurement data for their hometown or location of interest, that was risky. But to sort of overcome that barrier of, gosh, I don't know how to access the data myself, we have for Unit 3.2 a PowerPoint tutorial provided with screenshots and steps on how to access and interpret these time series for all 6 of the methods for whatever location you pick. And maybe you're going to pick your local area, and maybe you're going to pick some other area of interest. So I just wanted to show you, if you go to that PowerPoint tutorial for Unit 3, what it's going to look like. So it's screenshots of step-by-step instructions for each of the 6 methods. And I chose vertical GPS as the example. Shows you how to find the database. So here's a screenshot on getting to the Plate Boundary Observatory page and then using that map to zoom into the station that you want. Once you get to the database, you're also walked through how to obtain the data for your desired location. And then finally, and this could be relevant for you and or your students, we've also given you instructions for each of the 6 methods on how you might interpret some of these data. So I'd encourage you, if you're going to do this in class with your students or maybe as a project or homework, that you check out this tutorial and also perhaps offer it to your students for support as they do this. What I wanted to spend just my last minute on are talking to you about some challenges inherent in using these materials and some potential solutions. And some of this is going to be repetitive. Like, for example, I have very limited class time. I don't need or want or can use 2 to 3 weeks of material. So in that case, like I said earlier, take only what you want from the module. I would also add that much of the module, if you want, can be completed outside of class as preparations, homeworks, or projects, if that's a better fit for your time constraints. Second, if you don't have access to a computer lab, like I said, Unit 2, which is High Plains and Western Mountain Watershed, can very easily be done using Excel. If you want them to make their own plots in Excel, that's available for you. But if that doesn't serve you, we have hard copies of all of the time series that are needed in that unit. If your students have never looked at a time series, what a wonderful opportunity for them to do so. And we have teaching tips and teaching descriptions, walking you through how to teach students to read and interpret time series. And then finally, my students would have no idea how to get stream gauge or GRACE or SNOTEL data. See the last couple of slides, and we hope that the support materials in Unit 3.2 will be beneficial for you. So I'm going to stop sharing my slides and turn it back over to Beth, but I'm available for the end if you have teaching questions. Thank you so much.
All right, so I'm going to just cover the last few slides here. So I'm just going to go to the website for a moment here. So if you are at the front of, oh, that would be the wrong tab. I have too many tabs. This is what the GETSI site is like, and the eyes on the hydrosphere here is the introductory level modules. My screen's a little squished because I'm on a laptop right now. There's majors level modules here, and we actually have some field-oriented modules for majors classes. But if we go to the eyes on the hydrosphere, if you're familiar with Integrate or GETSI modules, this will look really familiar to you. But we have a front page that sort of goes over a summary, the table of contents, and a few particular strengths like make the students build their own water cycle knowledge instead of just getting all the arrows put on there for them. And then we have the different units. And within a given unit, the teaching materials are arranged in a very consistent way. So we have a summary at the top, learning goals, the context for the use. It's linked to the next generation science standards, which might be important if you're doing pre-service teachers. It also is linked to literacy principles, if that's something that your department follows more broadly. And then there's the main bulk of it is the description and the teaching materials themselves. So some possible readings in addition to the Western ones. the different exercises. And I don't know if anyone was following the chat box, but you'll see that we did actually add humans into the water cycle based on that being recommended as the best practices now. And here's a black and white version, which might be easier for writing on. And then all of the different readings for the students to learn about the methods and discussion questions and assessment questions that are behind an instructor firewall, so that you can, if you're already known to CERC, you'll be let straight in. If you're not known to CERC, then you'll just have a little verification process where I get an email and I check that you're real, and then you'll have access to instructional materials after, like answer keys and things. So that's how this works. There is also a student page, which isn't quite live yet, but it will be soon, an assessment page on summative assessment and instructor stories showing the way it was pilot tested in different courses. I think at the moment there's just one, but all three will be up there shortly. So that's just a bit of what the web page itself looks like, but now we want to make sure that you get a chance to ask us questions. So using the chat box, if you have any questions about the teaching for the method or the module, or methods and applications, the sort of the traditional geodetic ones, please feel free to ask questions. Let's see. Oh, and the link there is in the in the chat box again. So happy to take questions related to teaching or methods, scientific methods. So we'll start to answer the questions as they come in. How accurate is the GEodesy data? I guess there's not a single accuracy you could give. For the vertical GPS, it's generally considered that a given daily solution will have, in vertical is a little less well known than the horizontal, will have something on the order of a centimeter or so of error, but uncertainty, but the over multiple years, it's able to resolve things at a rate of millimeters per year. So I'd say we're on the sub-centimeter knowledge for the vertical GPS. Something similar, maybe a little bit higher uncertainty for the reflection GPS. And the GRACE data is averaged over, which I think gets to the next question, over fairly large areas. Let's see if I can, oops, if I can jump to, it's like several squares, per state kind of a thing. So it's quite large on a side, and there is of course uncertainty in how it's processed. But on the other hand, I think you could say that the changes that it's observing are quite robust and have been found with multiple multiple processing finds the same thing. Okay, thank you. Somebody was able to get in. It's about 300 square kilometers. So I was going to try to pop up a map, but I seem to be having trouble showing things with so many screens going on. So I don't want to spend too much time. Okay, you want to take another one?
Yeah, the maximum number of students in your class where you can comfortably handle this module. It's a great question. And I think it's, there's another question a little bit below that in the chat box about how to introduce this to a very large enrollment, presumably lecture class with then a whole bunch of lab sections and multiple instructors. So as a slow processor myself, I don't think that that's going to be something that I can answer in the 7 minutes that we have left in the webinar. So I'm going to chew on that and see if I can get a more coherent answer back to you once I think. But the short answer to this question about the maximum number of students where you can comfortably do this. I think for Unit 1, for example, where you're doing that jigsaw activity, I've done this in classes up to 36 students and have felt quite comfortable. In the jigsaw part in Unit 1, you are well within your rights if you have, a class size where it makes sense to form larger groups where there's maybe like 2 GRACE people, 2 SNOTEL people, etc. You certainly could have like a tag team situation where students are explaining the methods to one another in larger groups. I think that looking at the time series of different methods together in Unit 1 could conceivably be done in a class of any size, so tiny to huge, if you do it as a gallery tour, because at that point, you can hang up as many different copies of the time series and questions as you want and sort of engineer the group size to whatever works for you. Unit 2, which is the High Plains Aquifer and Western Mountain Watershed case studies, that could conceivably, again, be done in as small or large of a class as you want if you want to do it as a lab exercise, because in that case, each student would have their own handout, and then they could work individually in small groups or in larger groups, depending on the configuration of your classroom. The multiple instructors teaching lab sections question, I think what's nice about the GETSI products is that they are modular. So if there's one instructor who's really into the High Plains and another instructor who wants to focus on the Colorado case study, although they're looking at different data sets, it's still fulfilling the same overarching goals and instructional objectives, and you're getting a strong societal piece regardless of what study area you pick. But I'll think more about like how you could Tetris this for a class configuration like that and report back.
Just real quick, I think people can see the map that I popped up just to answer, give people a visual on the size of the squares, if you will. It's definitely a course grid for the GRACE, but super powerful nonetheless. There's another question, is the module suitable for graduate students? And so I would say this would be a case where if you go back to the GETSI website and page down a little bit, so again, this is circ.carleton.edu/GETSI, there is a majors level module called Measuring Water Resources with GPS, Gravity, and Traditional Methods. And it was really the impetus for this intro level module, but they simplified it and they sort of featured the parts they thought were relevant for intro. And I'd say if I was going to be doing this with grad students, I would probably do the majors level one and maybe even up the game a little, like make them go to the portals and download the data themselves instead of getting the sort of prepared spreadsheet data sets. There'd be a variety of ways to handle it for graduate students, but I would start with the majors level module.
And then I'd like to address really quickly that question about how do you deal with students that skip one day of class and come the next, because that could be a disaster if all of a sudden a group doesn't have a reflection GPS representative for the discussion, for example. The way I've dealt with this from learning the hard way multiple times is that I don't really do the GETSI stuff in its entirety back to back. So I might give a preparation exercise a week before, and so I'm going to see students another time before we're actually going to use it. And then maybe that next class meeting, I'm going to do a non-GETSI exercise on some other component of the hydrosphere. And so kind of peppering the GETSI materials in between non-GETSI stuff allows for people to be absent and not ruin the jigsaw activity that I'm trying to implement. So I would say just distributing the preparations more in advance than just the class meeting before might lead to greater success in that absence issue. It's a great question.
Thank you so much for your participation. It's been great to have such an interactive group. Just wanted to mention upcoming on the NAGT webinar series in late March and in late April, there'll be 2 more GETSI webinars. These will be more majors level materials. One is going to be teaching landslide analysis, and the other is going to be modeling flood hazards using HECRAS. Which is a professional software actually. Next week on the NAGT series, we'll be learning to integrate NEON data into your undergraduate class, and NEON, I forget the acronym, but it's like ecology network, and EDI resources. So it would be great if you could take a couple minutes to fill out the webinar assessment. So circ.carleton.edu 235-992, also in the chat box. Thank you so much for your attention.
Thanks, everyone.